Last time we talked about the Jacobi iteration for solving system equations, and we mentioned that for the Jacobi iteration to converge, we have it converges for a very important class of matrices called the strictly diagonally dominant or SDD matrix. Okay, so the definition is that the SDD matrix is the diagonal entry on row I is strictly greater than the sum of the off-diagonal entries on row I. Okay, so today we're going to keep on talking about that. So example, our matrix from the first example is this one. This is our matrix A. So let's see if A is a SDD matrix. So the diagonal here is 5. So we check 5 is greater than the absolute sum of the first row. And we check the second row. Absolute value 4 is greater than the sum of the other two guys. And the diagonal value here is 6 is greater than the sum of the off-diagonal entries. Okay, therefore A is a SDD matrix. And we have a theorem says if A is SDD, then the Jacobi iteration converges. Okay, so here I want to point out that this is only a sufficient condition, but it's not a necessary condition. What does that mean? It means if a matrix A is SDD, then the Jacobi iteration converges, but the reverse is not true. That is, for a matrix the Jacobi iteration converges, it's not necessarily guaranteed that the matrix is SDD. Okay, so for the Jacobi iteration, we know that it is a fixed point iteration that can be written in this form. And we know if we write the Jacobi iteration in terms of matrix notation, it is of this form. And the D is the diagonal terms, and L and U are the lower and upper triangular terms. Okay, so we have this is my Jacobi, this is our Jacobi iteration. And the B is called the iteration matrix. And if we do the iteration multiple times, we end up with a relationship here. Okay. So if AX equals B, then the error vector is obtained by the difference between the approximation and the case iteration minus the exact solution. So we define this as our error. And if we rearrange terms, we get xk equals exact solution plus the error term. And from the fact that x is a fixed point of this iteration, so x equals bx plus d, or the same as x equals b. And if we substitute x with, if we look at the Jacobi iteration, we will have x k plus 1 too bad. The writing is not very good. X k plus 1 equals b xk plus d. Okay, and we know that xk is given by x plus ek, therefore xk plus 1 equals x plus ek plus 1 equals b, and xk is given by x plus ek. So that's why we have this relationship. Okay, and okay, so and then we're using the fact x equals bx plus d, we can cancel the terms, and then we end up with this error equation, that is ek plus 1 equals bek. Okay, and if I keep on, so ek plus 1 equals b, so basically the newer approximation equals the error of the new approximation equals matrix B multiply the error of the previous approximation, right? So if we keep on doing this, then we end up with the the error at the k step equals the matrix B multiply k times k's power multiply initial error. Okay, so if we want to show that the method is convergent, we want to show that the error ek goes to 0 as k goes to infinity. So before we show that, let's derive some useful results that will be used. So we know that the norm of bx is less than or equal to the matrix norm multiplying the norm of the vector. So we had these results before. And so b squared x is therefore bounded by, so we use this twice, b and bx, and then use it again. So we got a b squared x. Therefore, we can say that the square, the matrix square, the norm of the matrix square is bounded by the norm of the matrix then square. Okay, and this can be extended to the nth power or k's power. Okay, so now let's go back to look at the error equation. So this is my error equation, and we care about its norm. So the norm of the error is bounded by the norm of bk multiply e0. So this should be bounded by the matrix norm to the k's power and the vector norm, and using this relationship, right? So we get the k's power, so we can move the k's power outside of this norm. So therefore this guy is bounded by b to the k's power of e0. Therefore, if we can show that the norm of b is less than 1, then this guy should go to 0 because it's less than 1, and the k's power of something that is less than 1 should go to 0 as k goes to infinity. Therefore, if we can show that, then we will have the desired convergence results. So motivated by that, we have the following theorem. This time this is a necessary and a sufficient condition for convergence of a fixed point iteration that is given by this formula here. Xk plus 1 equals bxk plus d. Is that all the eigenvalues of matrix B has magnitude less than 1. Okay, so let's, in case you forgot what eigenvalue is, in linear algebra we've learned eigenvalue satisfy the bxi equals lambda I multiply xi. So if this relationship satisfied, then we say this lambda I and xi are eigenvalue and eigenvector pair. So lambda I is called the eigenvalue, and this vector satisfy this equation is called the eigenvector. Because we want all the eigenvalue of b to be less than 1, it's the same as we require the largest of the eigenvalue to be less than 1, right? So therefore we define the spectral radius of a matrix this way, and that is defined as the maximum of the absolute value of all the eigenvalues. So if we require the spectral radius of the matrix to be less than 1, then we will have the convergence of this fixed point iteration method. Okay, and this is true for if A is a SDD. Okay, so therefore we have this result, Jacobi. Even if A is not SDD, Jacobi will converge if the spectral radius of this matrix B is less than 1. So here is an example. We're going to show you to see what happens here. Does Jacobi iteration converge for this matrix? Let's first check if A is an SDD matrix. So here, this is 4. Diagonal is greater than the off-diagonal entry. So this first row is okay. And the diagonal here, 3, is greater than the off-diagonal entry. Is okay. So this is an SDD matrix. Therefore, the Jacobi is convergent. That's correct. And let's look at this guy. So this is 2, is less than off-diagonal. And this one is 3, is greater than off-diagonal. Not all of them satisfy the SDD condition. Therefore, this is we cannot say this is not SDD. So therefore, we cannot say whether or not this will converge. Okay, so now let's look at the spectral radius of this B matrix to see if that's true. Okay, so we'll decompose A into L plus D plus U. So the lower part, diagonal part, and the upper triangular part And the B, we know that is negative D inverse L plus U, and we can easily compute that since this is 2 by 2 matrix. And we got our B matrix that is here. Okay. And it's easy to see, we've told you how to compute the infinite norm, so absolute row sum. So B infinite norm is 2, that is greater than 1. 1 norm is 2, that is also greater than 1. We cannot say whether or not this condition is satisfied, right? The norm is less than 1. But by looking at the spectral radius, we consider the eigenvalues. So to solve for the eigenvalue of a matrix, we solve for this equation, bx equals lambda x, and by removing that part, we're solving this determinant equals 0, and the determinant gives this characteristic equation, and by solving for that, we got 2 eigenvalues, and therefore if we check the maximum of all those two eigenvalues, they are less than 1, and we can say that the Jacobi matrix, the Jacobi iteration is indeed convergent. Okay, so this part, this example is not very obvious because it's not SDD, and we have to be very careful to find all the eigenvalues and check whether the largest eigenvalue is less than 1. Okay, so here is just some code that show you how we can implement this Jacobi iteration method for solving system of equations in MATLAB. Okay, so I think that's it for today.